This is a question on a graphical representation of sound waves, and it can be quite intimidating if you're doing this for the first time. So let's go through this together. The answer to this question is D, and the first thing that I will do is to identify the compressions. Compressions are easier to identify. You can see that this point is compression because the neighboring particles are very close to each other. So this is particle E at this point in time is at a compression. Okay, now same thing, particle M is at a compression also because the neighboring particles are very close to M. So that is the first thing that I will do, which is to identify just compression first. Alright, rarefaction is a little bit more difficult because the concept is similar. You have to look for a particle where the neighboring particles are very far from it. That's the idea of low pressure, low density. So that's rarefaction point. So particle I over here, you see particle H and J, they are quite far away. So particle I is rarefaction point. Same thing for particle A. It's a little bit harder to see rarefaction. It's not impossible, but it's a little bit harder. So I always start with identifying compression first. Once I got these two compression points, I will know that in between the compression points, halfway through that must be a rarefaction point. So I always use this trick to help me identify rarefaction point because they are in the center of two compressions. So that's a trick that you might want to write down if it's helpful. Now, after I've done this, then I can actually figure out what's the wavelength. A wavelength is just from a rarefaction point to a rarefaction point, or compression to compression. You can just calculate the number of boxes: 1, 2, 3, 4, 5, 6, 7, 8, 8 big boxes, and each big box represents 5 cm. That's why you get 40 cm as the wavelength. Now, amplitude. Why is this? How I will find the amplitude? Amplitude is the maximum displacement. So if you notice here, particle A is at the equilibrium position. So the displacement is 0. If you look at particle B, right, it was here, equilibrium position, but now particle B has moved 2 small squares towards the right. Particle C was here at this equilibrium position, but at this point in time, it has shifted 3 small squares towards the right. Particle D was at here, equilibrium position, and it has shifted 2 small squares towards the right. So therefore, 3 small squares is the maximum distance at this point in time, and therefore this will be the maximum displacement, and this will be the amplitude of 3 cm. Now you can apply this on any segment. I can apply this analysis on this segment. Look at F, it is displaced 2 small squares towards the left. G is displaced 3 small squares, so on and so forth. You will still arrive at the same maximum displacement being 3 cm.